Well, thank you so much. It's a real pleasure to be here and a real honor to be able to be part of your celebration. I was extremely pleased to hear your Vice Chancellor speak about the way in which uh, your university was focused not just on educating the students while they were there, but also with a bent towards lifelong learning. And that really is what I would like to talk about. So let me pull up some slides that will at least remind me of some things that I want to say. Um, my screen sharing has been disabled.
So enable, you can try now.
Okay. And let's see, which one do I want? This one. And let me back up. So I'd like to learn, like to talk about, how to focus your attention on learning how to learn. And my I'm reminded of this by one of my co-founders at Ginkgo Bioworks and a former graduate student of mine. While she was finishing her PhD at MIT, she came up to me one day and said, Tom, I'd really like to understand more about, I've forgotten exactly what it was, noise margins in digital circuits. And what class should I take to learn about that? It's really something that interests me a great deal, and I'm trying to figure out what MIT class I should take to learn more about that. And what I told her, and what the real message of the day from my standpoint is you don't need a class to take, to learn a specific thing that you want to know more about. The real skill, especially as you graduate and you go into graduate school, the real skill is, learning how to teach yourself about new subjects. So, your university is, expert, I assume, and have no doubt whatsoever, is able to teach your students all about calculus and physics and biology and economics and business and music and dance, and you can bring the students up to some fundamental level of understanding of any of those subjects. But my message of the day is, there's something even more important that you can and really, I think, have to do with your students. And that is to teach and motivate them to learn how to teach themselves about these subjects. And not just those subjects, but all of the other subjects that you don't have a class for, and that you will never have a class for, because it's too specialized, it's too unique, or the students may not want to know everything there is to know about some subject. They may want to only know a little piece of that subject. So, and the reason I'm telling you all of this is because this is my life experience, and I'll talk a little bit later about how I applied some of these things to my own education, which I think is a demonstration of some of these techniques. But the real trick is how if you want to learn about a new field, if you graduate with a PhD, or even if you graduate with detailed knowledge of some undergraduate curriculum, the chances are that you're going to know everything that you want to know in order to do some new job is very, very small. especially if you're doing a PhD. It's a very narrow subject that you're looking at, and when you get hired, in a company, or even if you go to a university and you study some other subject, you really have to be able to figure out, to orient yourself in that new field. I like to think about it, you're parachuting into a new field, and you need to orient yourself and figure out, what's important to know, what's not important to know. And, so a lot of questions come up immediately, and, you should be prepared to think through some of the answers to these things. What are the introductory texts? I knew no biology when I in 1990, when I decided that, really I needed to know about biology. And, so figuring out, what the texts are that are important, who wrote them, what technologies do I need, or what are the tools of the trade of that new field? How are they applied? Very important often is, what's the history of the field? Who did what, when? Why were things done at a specific time rather than, earlier or later? What were the pieces of critical understanding or equipment that made it possible to do things at a specific time? Why wasn't it possible to do it 10 years earlier? One of the things, and this comes out of my, sort of engineering mindset, and, other people will have other points of view, but I find it extremely important and very, very rewarding to think about the simplest possible version of each of the systems that you're looking at. And, if you really, truly, deeply understand the simplest versions of these systems, then, and think about, explicitly think about, what could I do that would make it simpler? What's a simpler example of the same thing? And, and you could collect those simple examples, and, it leads to a deeper understanding of exactly what's happening. So all of those are tricks that you can use to kind of, orient yourself in a field that you've never approached before. I have some tricks for reading textbooks. And, I think as an undergraduate, I always had the assumption, the professor assigns a textbook. You start on chapter 1 of the textbook, or ideally on the preface, and you go through to the appendix at the end, and you understand everything that's in there, and maybe you do the problems at the end of every chapter, and if you're a good student and you get an A in the class, and then maybe you promptly forget everything. So if you're trying to go into a new field, several things are wrong with that approach. First off, you don't have a professor to tell you what textbook to pick up, so you better be able to figure that out yourself. Secondly, 90% of the things that are in that textbook probably are not things that really interest you or really are relevant to what the focused questions you are trying to answer. You may come back and read more of it, but there's really only going to be maybe a chapter or two of that textbook that really is going to be the focus of your attention. What I found to be the most useful technique is to read not one textbook at a time, but rather a collection of a half a dozen. You get all of those textbooks and you compare what has been written on the same subject by many different people. And, it's important that those textbooks be written usually by one author, or at least originally written by one author, because what you're trying to do is you're trying to get into the brain of the person who wrote that book. You're trying to understand how they approach the subject. And it's going to be different from the way that some other person approaches that subject. And you want to be able to understand and articulate what those differences are and to get many different points of view on the same subject. So if you want to find out about, I don't know, ribosomes, which is something that, at one point I would have been very interested in understanding, I wouldn't want to find one textbook to read about that. I would find, a half a dozen. If you don't understand something, that's okay, because you can come back and you can look at it later. And what's important is, that you kind of get that overview of orient yourself in the field. I tend to look at the figures and the pictures in the book. It sounds juvenile, but it's the reality. You can tell a lot about what is being said in a textbook by looking at the pictures, and I do that. I'm not ashamed of that. I also only read the things that really interest me. And, life's too short to really study these things that, I don't care about. I'm not going to take a test on this stuff. I don't have to take a test on this stuff. That was when I was an undergraduate. And, it's important to give yourself the freedom to not understand or worry about the fact that you're not understanding something on a first pass through things. So those are some things that I have found useful. You have to orient yourself also by knowing who the people are. And it's extremely important to know whether you're reading something that was written by some first-year undergraduate student writing a review paper, or whether it's a Nobel Prize winner who is articulating his deep thoughts about how a subject should be thought about and articulated. You want to know where the good work is being done in some subject. There are places in the world that really excel, and it isn't necessarily the top universities that you would think of at first blush. If I want to know about Bacillus subtilis, I don't look at MIT or Harvard or Caltech or Berkeley. I look at University of Nottingham in the UK, and so be selective about where you're looking, depending on what the subject is. Think about what's happening in the field. What are the new techniques? What are the ways in which the field is changing? And again, go back and look at the history of what happened. Think about why were they able to do it now? Was it because they were better funded? Was it because somebody suddenly thought this was an important thing? Was it because of some breakthrough in the technology? We've had remarkable breakthroughs in biology with the basic technology, and so I look back, for example, at the understanding of basic biochemistry, and basic biochemistry was essentially figured out almost entirely in the 1930s. And it was done really with, essentially zero modern equipment. The tools they had to do it basically were good organic chemistry and radioactivity. And they were able to apply radioactivity and their excellent skills in organic chemistry to elucidate remarkably complex interactions in biochemistry. Only much later did we get much more powerful tools like chromatography, like high-speed centrifuges. Each of those novel developments ended up with Nobel Prizes, and they've made things an awful lot easier. But it's important to go back and think about how some of these developments were achieved with minimal equipment. And this goes back again to something I said before, which you should be thinking about what's the simplest way of doing some of these things. And simplest is not necessarily, oh, I'm going to go buy the latest magic piece of equipment. It may be using your knowledge of other subjects like organic chemistry and apply those, and you're able to do things that maybe will surprise you. Figure out where the activity is. Who are the people who are really driving the field and doing the exciting new things, publishing the breakthrough papers? And when you do that, you can go and try some of these things out yourself. Get your hands dirty. This was the way I learned a whole bunch of stuff. It wasn't by sitting in some classroom and learning differential equations. It was by taking things apart. When I was a kid, I took apart television sets and radios. These days, you take apart, computers. You figure out what all those pieces do, and try to figure out how you might be able to do things differently, how you could reassemble them in a different way. The bad news is in electronics, that's becoming much more difficult because everything is miniaturized, everything is glued together. It's much more difficult to take things apart. But that isn't true in some of these other fields like biology. You can take things apart in biology, and you can understand how things work. So there's a real value in getting your hands dirty. It used to be that that kids grew up and learned how to repair automobiles. Maybe they still do. I think there's a lot to be said for that. Can you recreate an old experiment? You've looked at some history. You've said, okay, those were great ideas, and were done in very exciting ways. Could you go and could you do that same experiment again? And we can we can go and we can think about how you would do that very same experiment, but not with the equipment which was available then, but with all of the modern equipment that you have. Something that is extremely important to say is that you're going to make mistakes. You're going to make errors in doing this. And the question is, are you going to be able to understand what those errors are? Can you recover from them? And can you do things in such a way? You of course have to be safe when you're working in any of these fields. Things don't always work, and they don't always work for lots of reasons. I think it's the case. In biology, we publish protocols, ways of doing things, recipes for how you can isolate pieces of DNA, for example. I think I have 100% record in saying that the first time I try out any of those recipes, they fail. Every single time. I have never, ever tried something and have it work the first time. So the question is, what do you do when that happens? What's your reaction? You could just try it again, and sometimes that works, and great. If that does, go forward. Usually there's other problems. Usually you are, not doing something quite right. The person who wrote the protocol may have not have been doing something quite right. The trick is to be able to identify the root causes. It's a little bit like, debugging a computer program. It doesn't behave quite in the right way. How do you figure out what's wrong with with the program? What's wrong with this protocol? And if you can identify what those root causes are, and especially if you get to a place where sometimes it works and sometimes it doesn't, you want to figure out ways to make it work always. And if you do that, you have really learned something, because now you've solidified your knowledge. You can update your network of knowledge, and so the next time you encounter something that's similar to that, the solution will be obvious. And that's a very rewarding and also a very important thing to be able to do. This is everybody says this. You really should surround yourself by people who know more than you do. So that was the great thing about being at MIT for 40 years. There was always someone around who was smarter than me. And, so you can, some of that rubs off. And, so you want to go and seek out the places in the world where you know less about something that you want to know about than your colleague that sits at the next desk. And if you can do that, you will pick up a lot of that knowledge. And you don't have to pick up all of that knowledge. You have to pick up enough of it so that you can do the things that you care about doing. And then, maybe you go and say, all right, now I know enough about, RNA polymerase. I go and I find the person who is, going to tell me about how ribosomes work. It's a different person. They also, they know more than I do about ribosomes, but now I might know more than they do about RNA polymerase. And, so you can move around through a set of people and, tap into their knowledge at multiple different levels and come away with a much broader perspective than you ever imagined. When you encounter people, you should be thinking about, how you can suck that information out of them. Find out what they're working on, what excites them. Tell them what excites you. They may have some ideas that you haven't thought about. Go to their meetings. If it's a famous person that, is in Amsterdam and I'm on vacation in Belgium, I'm going to go and I'm going to visit the person in Amsterdam, and I'm going to figure out all the things that, I want to ask that person because, he knows more than, or she knows more than I do. Offer to give a talk. It can be a two-way conversation. And, if you engage other people with what excites you, then, they are more responsive to telling you the things that are exciting to them. This is an extremely important, notion, this idea of building your network of knowledge. So my mentor, Marvin Minsky, who is one of the founders of the field of artificial intelligence, had a saying, and he said, "It is a very poor kind of understanding if you only understand something one way. You really want to understand things in multiple different ways. And if you don't understand things in multiple different ways, then you're missing out on a lot of that understanding." So this diagram kind of gives you a picture of that. Things come in on the left, there are pieces of data, and you might want to you're going to be able to take that data and associate that data with well, what kind of sample was that, or how was that collected. You get information, but it's not something that you can that you in any sense have analyzed or understood. It's only when you connect those pieces of data together and build a model of what's happening in the world that you get to that stage of aha, I sort of understand what's happening. And then but the more you do that, the more the more you're able to connect the information that's coming into these networks. Then at some point your networks become richly connected with one another. And when the networks become rich enough and connected enough, you're able to see connections between different parts of your network that you never imagined. And this is really where you move from understanding a subject to starting to have insight about a subject. It's where you're able to connect things that other people may not have ever connected together. You're able to apply an idea that came out of electrical engineering and apply it to a field like biology. Those are the insights that you want to develop, and it only comes if you're able to richly connect together the knowledge that you're acquiring. I think, and I believe Marvin Minsky also believed that the quality of these networks that you're building up internally in your mind are really what makes some people smart and other people not so smart. The smart people really have figured out how to make those rich networks and to connect all of the things that they know into a coherent vision of how the world works, and how they can influence it, and how one aspect of the world influences and can be leveraged to better understand another part of the world. And this is a critical skill that you need to develop. This was a lesson that I learned, and I didn't really learn this until I was teaching at MIT, but others already know this. The best way that you can learn a subject is to try very hard to teach it to somebody else. And there is nothing that will expose your lack of knowledge about a subject as much as an attempt to teach it to someone else. Because when you try to teach it to somebody else, what happens is it exposes immediately the fact that you don't really understand it very well yourself. There's a story that goes along with this. You might think, well, all of the professors that teach in my class, they know this stuff cold, and they're just telling me things that they've known for the last 10 or 20 years. I'm here to tell you that's not true. This is a dirty secret of the professoriate. Some of those subjects that they're teaching, they're probably learning them along with you. And there is nothing, I can tell you, that is quite so motivating in terms of learning a subject to realizing that you are going to have to stand up in front of a set of undergraduate students and make a fool out of yourself. And so it is highly motivating to and encouraging for you to learn a subject very rapidly if you know you're going to have to go teach it. So, this is a technique that is remarkably effective. And when you're doing this, you don't necessarily have to start by teaching other people. You can try it out by teaching yourself. You can write down a lecture to yourself, where you try to explain, by writing it down and making it clear to yourself exactly what's happening. And when you try to do that, you'll realize that there are these big gaps in your understanding. And this is when you can go back and you can start reading that textbook again, because you're going to be motivated now to go back to that textbook. You're going to know what it is that you don't know, and you're going to be able to find it in those textbooks. You're going to be able to find several different versions of it in that textbook. And when you really understand it, then you're going to be able to link all of that new knowledge that you have into that deep network that you must be building up. The bottom line is that, if when you try to do this, if it's not completely, utterly, totally, ridiculously obvious to you, you don't really understand it. And you don't want just one explanation for something. You want, as many as you can find, at least two. Think about two very different ways of understanding exactly the same thing, because that's going to be the key to getting into your linked network. And it's going to be adding those links in your network that let you connect different ideas in different sorts of ways. Feynman, is a big exponent of this, and there's this website that talks very thoroughly about the technique of doing this. But this is the most powerful technique for learning something, is to try to teach it either to yourself or preferably to somebody else. So some suggestions from Richard Feynman. Richard Feynman, of course, is a famous physicist, and I had the privilege of actually knowing him briefly towards the end of his life. But he left a legacy of really some very good suggestions, and so these are some of his. Read every day. There's no excuse for not learning something every single day. Go out into nature. Look at things in the real world. Look at the flowers. Stare at the clouds. Listen to the birds. Ask questions. Don't ever stop learning. Don't pay any attention to what other people think of you. Are you a nerd? I was a nerd. I didn't care what other people thought about me. And, that I think that most of the people who are really engaged and self-educating are in that category. Do the things that you care about and that you're interested in. Of course, teach others what you know. Make mistakes. Don't be afraid of making mistakes or making a fool out of yourself. It's okay. You don't have to know everything. There's a quote by one of the more recent physicists, Jennifer Cooper-Smith. Let me try to get this right. You can know anything. You can't necessarily know everything. And so, you have an ability to learn any subject that you put your mind to. You will never know all of the things that are out there so you can be selective about what it is you want to learn about. And that's a wonderful thing because, you can become a person who is an expert in one field and, be a colleague of people who know about things in other fields. I thought I'd end just by, giving you a little bit of a picture of, how this affected my life. And, when I was in high school, there were essentially no computers. There were large mainframe computers that, had punch cards on them. I discovered computers at MIT. I was a local boy at MIT. And so in high school, I discovered that, there were these marvelous things called computers, and you could program them and they would do the things that you cared about. And they would do the same, you could tell them what to do and they would do them. That was really quite an amazing thing at that time in my life. And, there was no way that you could educate yourself in computing at that time. There were no courses in computing. There was no undergraduate major at MIT or anywhere else in computing. I had to teach myself how to program. I had to teach myself about operating systems and interfacing hardware to computers, how they worked, and really got into the details of that. So that was really the first time I sort of taught myself, without a lot of help from some collection of teachers. I got my electrical engineering and computer science degree at MIT, but I have to tell you, despite that, I was not a proficient electrical engineer at that point. I was not good at electronics. That didn't happen until later, when I decided that it was important to understand how semiconductors worked and how semiconductor design was done. I did that by taking things apart. In particular, I took apart integrated circuits. I taught myself all of the design process for pieces of silicon, and ended up teaching the MIT class in that. As part of teaching that class, one of the things, this would have been in about 1990 or so. And in about 1990, I was teaching that class in semiconductor design at MIT. And the first assignment I gave to the students was, students, you've all heard about Moore's Law. And Moore's Law is this wonderful law which says that, every year or two, the size of your, silicon integrated circuit, shrinks by a factor of 2. The power goes down, the speed goes up, everything is better. And, it's been like this for the past, 10 years, and looking forward, what's going to happen in the future. And I said to the students, okay, you know where we are with semiconductor technology today. Tell me when that exponential improvement in technology ends. And, the answer is, it ended, about, in, 2017 or so. And, you could predict when it would stop, because all exponentials of that kind stop eventually. You can't have something that's an exponential that goes on forever. You could predict when it would stop. And you could then ask the question, why did it stop? It stops, crudely speaking, because you run out of atoms. Simply, you can't keep shrinking, a semiconductor device until there's, when you've got it small enough, you don't have enough atoms in that device. And you could predict when that was going to happen. And as I said, it has already happened. That was part of the thinking that, sort of led me to say, all right, this semiconductor stuff is really powerful. It's been doubling in performance, for the past 10 years, and it looks like it's going to double in performance for the next, 20. That's, I should be happy about this as a technologist. I should be pleased that, I can go and I can design semiconductors for the rest of my life, and I will be rich and famous doing that. But instead, I guess my reaction was, oh my God, this is, we have to start thinking now about what's the next thing. What's going to happen after we run out of performance in silicon? And that's one of the things that got me started in biology. So in about 1990, for a couple of different reasons, this was one of them. Another one was you have to understand that at that point, no undergraduate at MIT was required to take any course in biology. If you were an MIT undergraduate, you took classes in physics and in chemistry and calculus and some humanities courses, but never, except for the biology and the med student, wannabes, you never took biology. And so as a result, here I was at 40 odd years old. And the only biology I had ever had was as a high school student. I was taught biology where they taught you the names of parts of flowers. And as a budding technologist, that really was not very interesting to me. And so I sort of ignored biology. When I did think about biology, I thought of it as this horribly complicated subject which I would never understand. And so it was a little bit of a revelation in 1990 when I went and looked back at the subject and realized that there were relatively simple kinds of biology. There were kinds of biology that you could understand, or at least that you could fool yourself into thinking that you could understand. Biology in general is very complicated, but for the simple organisms, for the bacteria in particular, you can pretty easily understand how they work these days. And you can start thinking about them not as this complicated God-given thing, but as something that you can take apart, you can put it back together, you can change it, you can program it, and that got me very excited about biology. So for the next about 6 years or so, essentially, I became a graduate student in biology. I took courses at MIT, and I read, hundreds, literally hundreds, probably high hundreds of textbooks on biology using some of the techniques that I've talked about today. I was, very tightly connected to the computer science and information technology groups at the funding agency in the United States called DARPA. And I convinced some of those people that, it was important to kind of go and start taking a look at the border between biology and computer science. And when I did that, I started doing that in a serious way, and eventually convinced them that they should start a program, which then, of course, I applied for funding under, to go and study this. And, I got them to fund a microbiology lab in the computer science department at MIT. My colleagues, I'm pretty sure, thought I was going to kill them. That was kind of fun. And, as was mentioned in my introduction, during that time, I created this student projects class called iGEM, and also set up this BioBrick standard assembly process. I also started educating a set of graduate students, and particularly along with my colleague at the time at MIT, Professor Drew Endy, who is now at Stanford. The two of us, both ran labs, in this emerging field of synthetic biology, and we educated, of course, a set of students. And so time passes, and in 2008, four PhD students were coming out of that program. Two of them were my students, Reshma Shetty, who I've already mentioned, and Austin Chi. And two of them were Drew Endy students, Jason Kelly and Barry Canton. The five of us, decided that it was time to see if we could commercialize some of these ideas. And so we started a company, in 2008. I have to tell you, I was fed up with academia at the time. I think there's there was a lot of I had a lot of disagreements about what was important or not important in teaching biological engineering. I was not having my my point of view well accepted. I was also having trouble getting funding. And so a combination of several of those things led me to be very excited about the idea of just starting a company, which we did. And, we started on a shoestring. We had no venture funding, no outside capital came into the company until about 6 years later in 2014. During that time, we funded ourselves with a set of government contracts of one kind or another. We set up a lab on the cheap. In 2008, some of you may recall, at least in the United States, there was a very large recession. So the economy was in tatters. That turns out to be a great time to start a company, especially if you don't have money. Because other companies are going out of business. And because they're going out of business, they're selling equipment. And so, I put a little bit of money into the company up front, somewhere in the $150,000 range, and it kept us going. But what was possible with that was that we could buy equipment for about 10% of the list price. And so we set up a lab with very, very low expense, and started doing work. Grew the company very slowly, and it wasn't until, as I say, 2014 when we started taking money from outside investors. So I think I'm going to stop there. I've said enough about about my life and where I've been and what I think are some of the important aspects of it, and take questions if there are some, and be happy to go from there. Oh, and one last thought. You can keep learning and learning, and pretty soon you learn something no one else has learned before. So that's a thought from Richard Feynman. So I thought that would be a pretty good place to end all this.